Hi, welcome to the statics tutorials. So in this example, we're going to look at some applications of the dot product. So this first part, we're going to use the dot product to find an angle between two vectors. So we have a boom that goes from the origin here out to point A, and then we have a force vector F that acts on the top of the boom. The force vector is given in the problem statement as 30I minus 40J plus 10K with units of kilonewtons. And for what we need to do, we'll need to also go ahead and get the magnitude of that force vector. So the magnitude would be each of the three components squared, add them all together, and then take a square root, and that gives you about 51 kilonewtons. Now for the boom, we'll need to get a position vector that goes from the origin out to A. And let me give you another way to think about position vectors, and either this method or the method in one of the previous videos works. Let's also discuss where we have these dimensions and how to interpret these dimensions. So the important thing with the dimensions, because there's a lot of lines here, look for the lines that have the little arrows on either end. So we've got a line here with arrows on either end, a line here with arrows on either end, and a line here with arrows on either end. Find an axis that's parallel to one of those lines that have the arrows at the end. So let's look at the x-axis. We're looking for one of those lines with the two arrows that's parallel to the x-axis. So x is going in this direction. It looks like this line is parallel to that. So the 3 meters is giving you the direction in the x direction. So you're starting at point O, you're moving out then 3 meters. So doing your position vector, you could think about this as being 3 meters minus 0, or you could think about this as just moving in the positive x direction 3 meters. Either way, it's going to give you 3I meters in your position vector. Now let's look at the next line. So we've got this line with the two arrows on it. We've got the y-axis that's parallel to that line. Y-axis in this direction, line with the two arrows going in this direction. This must be our y component distance. So if we started at the origin, we came out over here 3 meters in x, then we're going to come out over here positive 7 meters in y. So we have 7j that we're going to put into our position vector. And then our last line with 2 arrows on it is here, and you can see this is parallel to our z-axis, same direction in z, same direction as our line with the 2 arrows. So that's our z direction. So we came out here 3 meters in x, 7 meters in y. We must be moving up now 10 meters in z, so we'll do plus 10k. We'll put the usual brace about the Cartesian notation, and then we'll put the unit of meters out here to the side. With the calculation that we're going to do, we need the magnitude of this vector. So it's going to be 3 squared plus 7 squared plus 10 squared. Add them all together, take a square root. We get the 12.57 meters. Now we can go ahead and use a unit vector, and that might make things a little bit easier for what we're going to calculate. So I'm going to go ahead and just calculate this unit vector. So this position vector has a length or magnitude of 12.57. I can give it a length of 1 if I divide it by its magnitude. So U for unit vector is going to be position vector divided by the magnitude of the position vector. So here's my position vector, here's my magnitude, and then to calculate this, remember we're just going to distribute this through each of the components. So we're going to do 3 divided by 12.57 gives us our 0.2387. 7 divided by 12.57 gives us our 0.5569. And then 10 divided by 12.57 gives us our 0.7955. So those are our 3 components. Then to get our angle, we can use our dot product. So our angle is going to be the inverse cosine of the dot product of our position vector with our force vector divided by the magnitude of the position vector and the magnitude of the force vector. But looking at this, we could say, hey, we've already calculated that portion. position vector divided by the magnitude, that's our unit vector. So we could also write this formula as the inverse cosine of our unit vector dot our force vector divided by just the magnitude of our force vector. And let's use this form of it. So here's our inverse cosine, and then to do our dot product, we're going to take each of the components and multiply them together. So the x component here is multiplied by the x component here. The x component here is multiplied by the x component here. Make sure that you include any positive or negative signs. The z component here is multiplied by the z component here, and that's here. So it's going to again be x times x plus y times y plus z times z. Add that all up, divide it by the 50.99, get a number, do the inverse cosine of that, and that gives you 98.1 degrees as the angle between those two vectors. The next thing we can do with dot products is we can determine the magnitude of a vector that's going in the direction of a second vector and the magnitude of the vector that's going perpendicular to that second vector. So if we think about this, we're breaking the force vector F up into parallel and perpendicular components. The Hibbler book just uses the symbol FA where the line is A, but you'll also see texts that just use the two parallel line symbol as well. So we could say that the parallel component is equal to F dot the unit vector going in the direction of the line, and so we get 7.16 newtons. That's exactly the same number that we calculated here that was inside of our inverse cosine, so I just brought it down. Typically you report this without the positive or negative sign. The negative sign just means that the way these vectors are aligned, the force vector has a slight component that's pointing from A down to O, versus our position vector went from O up to A. So it just has the opposite sense of ROA. We can calculate the perpendicular component. It's equal to the magnitude of the force vector squared divided by the magnitude of the parallel component squared, and then you just take a square root. It's just the Pythagorean formula solving for one of the legs of the triangle. So the perpendicular portion gives us 50.5 newtons. You can see that our angle is close to 90 degrees, which means that these two vectors are close to being perpendicular, but not completely perpendicular. And that's resulting in the parallel portion being fairly small and the perpendicular portion being almost the same magnitude as the overall magnitude of the force vector. Thanks for watching.